Okay, so this paper is called The Bidder Exclusion Effect. This is joint work with my co-authors Dominic Coey and Kane Sweeney, who both were at eBay Research Labs when we worked on this and don't have their updated affiliation. So I should mention first this, so give an overview of this paper. What we're trying to do is provide a new tool for the analysis of auctions, really useful for certain questions, and has the virtue of being trivial to compute relative to what most of the empirical auctions literature requires you to do in order to answer questions in the structural auctions literature. So let's jump right into it. So the empirical work in auctions often requires some kind of a complex estimation technique, and I'm not trying to criticize them. I think they're really cool, actually. I like all the progress that has been made, and I think they're kind of fun the way that you tie in theory so closely to the empirics. But here's an example of a question you might want to answer would be, how would the seller's revenue improve if the seller were to use an optimal reserve price? And to answer this, some typical assumptions would be things like bidders are symmetric, they have private values, their values are independent. The number of participants in the auction is independent of the bidder's values. So this is like the number of bidders is exogenous that arrive and participate. The number of participants is correctly observed, and you've got data from non-binding reserve auctions. So you wouldn't have to make all of these necessarily, but these are typical assumptions. What we propose is an alternative approach to answer that particular question and some other questions as well. And we call this tool we introduce as we call it the bidder exclusion effect. So we're defining this new. This is not an effect defined before. This is something we're just stating, and we'll explain why it's. I'll explain why it's why you should be interested in this. So the bidder exclusion effect is the fall in expected revenue if you were to exclude one bidder randomly from the auction. So just take them away from the auction. First of all, it's easy to calculate. You can compute this without any sort of complex estimation technique or without requiring instruments, or you can find bounds on it, even if you can't compute it directly. You can do it even if you have correlated or private, where they have correlated values or common values, correlated private values or common values, asymmetries, unobserved heterogeneity, unknown number of bidders. You can still get bounds on this thing. And it gives us some insight into some interesting issues. So first of all, whether we should think of bidders' values being independent of the number of bidders. So how should we model entry here? Should we think of the number of bidders that are there as independent of how much they value the good? Or how the distribution of valuations among those bidders. Also, how much reserve prices matter. And we tie this into the Bulow and Klemperer theoretical result in the 1996 paper. And then also we've fleshed this out a little bit in this more recent version of the paper. What are the seller's losses, or can we get some bounds on it from bidders colluding or from bidders merging? And the data requirements here, there's a typo that should say third highest and second highest bids are the ones. In ascending auctions, there's this, in the literature, some people will refer to the highest bid as being something that's unobserved. It's the dropout point of the highest bidder. That's how I'm going to use the term. The first order statistic, the max order statistic, is this unobserved one. So second and third order statistic means the two highest observed bids here, if this were a button auction. And we'll describe the extensions to other settings as well. So this is related to a variety of different papers. So first of all, it's related to this idea of sufficient statistics for welfare analysis. We're sort of plugging in and there's some of the papers there. Many of you are in this room that work on this literature or have contributed to this, and we're just sort of filling in a gap there and saying, you can do this in auctions too. There's some cool things you can learn just using about structural objects without using some sort of complex estimation technique here. And then a wide array of the auctions literature that we're contributing to here. In particular, that last bullet point, trying to get at auctions results with just using bounds, using revealed preference arguments is the way Hale and Tamer and looked at it. And then Ardiaz, Lopez, Gandhi, and Quint exploited some fun order statistics relationships. And that's kind of what some of our results will rely on as well, some of these fun things you can do with order statistics. And we're going to focus, we focus in the body of the paper on ascending auctions as our illustrative example, but we talk about in the appendix how you can also extend this to first price auctions and other settings as well. So to illustrate the bidder exclusion effect, what we mean by this then, and how you could compute it easily, consider first just a private values sealed bid second price auction, and we'll explain how you don't need all those assumptions, but it's easier to illustrate it this way to begin with. So each of these tick marks just represents order statistics of bids. So these are the dropout points that the most that bidders would be willing to pay. And that's going to be equal to their values in the setting of a private values sealed bid second price auction. The red mark is going to be what the seller's revenue will be, the second order statistic of the bids. If you were to remove one bidder at random, there's some chance that it would be some lower guy there up in the top line there would be some lower, one of the lower statistics, and that would not change revenue at all. If that were the guy that got removed at random, it wouldn't change revenue. It would only change revenue if you removed one of the top two guys, in which case revenue would drop to the third order statistic. So the chance that if you remove a bidder at random, you're going to pick one of the top two guys is 2 over n. And the chance that you have revenue unchanged is n minus 2 over n. So we can just easily compute the bidder exclusion effect in this setting as 2 over n times the expected gap between second and third order stats. What's nice is that didn't require that bidders be symmetric here. It didn't require that their values be independent. This is just a very simple thing you can compute from your data, just looking at the second and third order stats. And it turns out that we'll show you can do this a similar thing even if bids are even if there's some sort of Hale-Tamer like low bidding, or even if there's common values or unknown number of bidders, you can still get bounds. Use the same idea to get bounds on the bounds on the expected drop in revenue from removing a random bidder. And you might think, well, why do I care about that though explicitly? Why do I care about removing a random bidder? And it turns out to actually be the thing you want to look at, the right thing for a number of questions. The effect of not just removing some particular bidder, but a random one of those that participate. So take that as given for now that you want to know that. You really want to know what's the effect of removing a random bidder. You might think that you could just do this just by regressing revenue on numbers of bidders, for example, and you'd see the effect on numbers of changes in numbers of bidders on revenue. That would work if the number of bidders is correctly observed, and if the number of bidders varies exogenously. But if it doesn't vary exogenously, you'd think you'd want some instrument there. But even instruments approaches aren't going to give you exactly what we want. We don't want a late here. We don't just want some local average treatment effect. We want to know really what's the average treatment effect of changing the number of bidders and of removing an actual random bidder. So just to illustrate that idea there of that IV approaches line there, this paper, one of the motivations for it originally was this project I was working on with Devin Pope and Justin Sidnor and Nico Lacetera on auctioneers at auto auctions, where we measure the effect. We have some quasi-random variation in the auctioneer, the human that's actually calling out the bids, and we use that to measure the revenue impact of having a really good auctioneer versus a bad auctioneer. How much does that raise the revenue? And that's a separate paper. It's really kind of a fun idea, but we wanted to be able to. We had some numbers at the end, and we said, well, here's the revenue impact, and people said, and we said, so maybe this is something that. So one of the takeaways from the paper is maybe there are other things we should take into consideration when we're thinking about designing or organizing. I don't want to call auction design the auctioneer, but it's another element of organizing an auction. You might want to try to get a good auctioneer there. Maybe it's even more important than what we think about as typical auction design. Was sort of one of the takeaways of the paper, and people said, well, we know already from the Bulow-Klemperer result, and just to review that if you're not familiar with it, the takeaway from the Bulow-Klemperer's paper is it's better to have one more bidder there, one more random bidder show up than to have no reserve price at all, than to switch from no reserve to the optimal reserve price. And so I wanted to be able to make this comparison and say, well, here's our auctioneer effect, and here's the effect of having a random bidder show up. And so I looked around for ways I could get some sort of instrument in the number of bidders there that I could move around. And I talked to the people at the auction house, and they said, well, you could try to use. They said we have sometimes like a barbecue that we host, or we have some sort of drawing right before particular auction sales, and that attracts more or less bidders. That's sort of a surprise when we do that. And I thought about it for a bit, and I thought, oh, it's really kind of a cool instrument. We could use that, but that's really not going to give us a random bidder. Those are going to be the guys that like barbecues, and that's why they go to the auction house. And so it's not what we want. We wanted to be able to compare this to this result from Bulow and Klemperer, and we wanted something that would really give us the effect of a random bidder arriving, an additional random bidder. And then it turned out as we explored it more and more, we found that there's a lot of other things we could look at in interesting auction questions that if you know the effect of a random bidder showing up, you can ask. So to overview our strategy, then I'm going to introduce some notation. So and this is we'll use it throughout the rest of the presentation here. So we write the order statistic. Bk out of n is just the order statistic as I've used already, so it's just the kth order statistic out of n. On the second bullet point here, k out of m comma n, what we mean here is the kth smallest bid in an m bidder auction where those m bidders were randomly selected from a larger number n. So if we randomly removed one bidder, is what you'd see here in this bottom point here, the equation 1 there on the right of that, the b to the m minus 2 out of m minus 1 comma n means what's the bid going to be when you randomly remove one bidder? What's the second order statistic going to be if you randomly remove one bidder from an n bidder auction? There are n bidders there. You randomly take one away. What's the counterfactual bid going to be? So this delta of n is the bidder exclusion effect. This is the expected revenue in the n bidder auction minus the expected revenue if you were to randomly take away a bidder. And that's a counterfactual object. It's not something we're going to observe in the data. I'll show you certain cases where it's equivalent to things we can observe in the data. But this is the counterfactual object that we're interested in is if you were to randomly remove a bidder and let all the other bidders know that there's one less bidder, how is bidding going to change? That's what's captured in delta of n. And we'll describe two other objects now that are things we can observe in the data. So the first object, this delta superscript bid, this is if you were to remove a random bid of the realized bids, not remove a random bidder and let them reshuffle. It's not a counterfactual object. This is just take away a random bid, and this is what I illustrated with those tick marks before. So if you remove a random bid from the n bidders, then the expected change in revenue is going to be 2 over n times the gap between second and third order stats. That's something we can just observe in the data if we observe n and we observe the second and third order stats of the bids. The bottom object here is the difference, is another one we're going to use a little bit, which is the difference in observed revenue between n bidder auctions and m-1 bidder auctions. And I should have been clear too when I say revenue here, we're assuming there's no reserve prices in these throughout the presentation here, and in the body of the paper we assume there's no reserve prices. In the appendix we talk about how you'd extend this to cases where you had auctions that came from binding reserve price data. But so this is revenue. The expected second order stat is the seller's revenue in m bidder auctions, and on equation 3 on the right there is the expected revenue in an n-1 bidder auction. So this is the actual observed difference between n bidder auctions and m-1 bidder auctions. So the three objects, these key objects then again are this first, the top one is this counterfactual object. We'd like to know the bidder exclusion effect. Then we have the expected drop in revenue from dropping a bid. And then we have the actual observed difference between n bidder auctions and m-1 bidder auctions. What we can do with those three is we can say, first of all, if valuations are independent of the number of bidders, so this is I'll go into more detail in a moment on this assumption, but describing it in more detail. But this is about the entry process into the auction, the number of bidders that show up. If that varies, if more bidders show up, or when more bidders are showing up, they're higher value bidders. Their distribution of bids is generally stochastically dominating that when there are lower bidders. Then we'd say entry is selective here, or valuations are not independent of the number of bidders. Is the terminology used in the empirical auctions literature. So if entry is selective, then the bidder exclusion effect, delta of n, should be not equal to the observed difference in revenue between n bidder auctions and m-1 bidder auctions. So that gives us this nice test for selective entry. For should we model entry as being exogenous, the number of bidders in an auction as being exogenous. Then we also demonstrate some conditions where delta of n relates to this, is going to be bounded above by the expected gap between the scaled gap here between second and third order stats, delta of bid. And that's one that we can relate to the Bulow-Klemperer result to get a bound on how much would a seller benefit from using an optimal reserve price. And then we can also relate it to bounding how much a seller would lose out if two bidders were to merge or two bidders were to collude. And so we'll go into detail on each of these applications. But first, to show you could extend this to various cases. So this is, if we first look at ascending auctions with private values and no reserve price, then this is the one I illustrated with those tick marks before. You can easily compute the bidder exclusion effect as just being equal to delta the gap between second and third order stats. That is the 2 over n times the gap between second and third order stats is the change in revenue from removing a random bidder. Excuse me. It's the same as removing a random bid. And you can easily compute this also conditional on any covariates you want. It's just a conditional expectation, which is convenient as well. If you have a setting of low bidding here, so this is similar to the Hale and Tamer 2003 setting where they say bidders might drop out below their values, planning on jumping in again later, but then they see that their bid gets passed, and so they never jump in later. Then if you have a setting like that, then you still end up with this 2 over n times the expected gap between second and third order stats being an upper bound on the change in revenue from removing a random bidder. And this is slightly different than the exact Hale and Tamer setting, but this is doing the exact Hale and Tamer setting requires some additional notation, and so we relegate that to the appendix. But you can extend our approach to to their setting as well. So this is, when we say low bidding in our paper, we mean cases where you bid lower, where the losers could have bid lower than their value. They might have bid lower than their value. So we also get an upper bound when we look at common values auctions as well. In this case, we limit to symmetric auctions, where just because things get super ugly with asymmetric common values auctions. But with symmetric common values auctions, then it also turns out that the bidder exclusion effect, the effect of removing a bidder at random, is bounded above, strictly in this case, by the 2 over n times the expected gap between second and third order stats. And there's some nice intuition here. So this is because removing a random bid, excuse me, and then assuming that all the other bids would have remained unchanged even without that bid there. That's what the delta superscript bid is doing. That's going to overstate the decline in revenue, because if there really were one less bidder there, the winner's curse would have been lessened, and there wouldn't have been as much shading. So you're going to get an upper bound as well, and it relates to these results. It relies on some results from this Bichandani et al. Paper, which shows that this is going to apply in any symmetric separating equilibrium. And as far as we're aware, it's a very simple argument, but it's the first. There really is nothing on ascending auctions with common values in the empirical literature, sort of any objects of interest you could identify. So this is one object of interest, and I still have to, I guess, convince you that it's of interest. But this is one object you can identify in common value ascending auctions, is a bound on the bidder exclusion effect. You can also get an upper bound even if you don't see the number of bidders. If all you saw was the second and third highest bids, and this is really convenient because that's all you see in a lot of settings, like in online auctions, like on eBay, ones that Ron talked about earlier. You never really know how many bidders showed up to the auction. You just see how many bidders placed a bid. But some people came up, they showed up, and then they just saw that their value had been passed, and they never placed a bid. So you'll see a lower bound on the number of bidders, but you won't see the true underlying number of bidders. And same thing with auto auctions as well. You don't really see in the data, in most auto auction data, the number of bidders. But if you have some lower bound, we call this little n lower bar. I don't know if I described this well. So capital N we're thinking of as the random variable, the number of bidders, and little n its realizations. So little n lower bar, if it's a lower bound on the number of bidders, then you can just throw that into the denominator instead. So 2 over a lower bound, you're still going to have an upper bound on the bidder exclusion effect here. It's just the bidder exclusion effect averaged over all the possible numbers of bidders. So now that I've shown you it's possible to estimate it, then I'll show you some examples of why you'd care. So there's this common assumption in the auctions literature. This is just going through the 3 examples I gave at the beginning in more detail here. So there's a common assumption that says that has different names, but these are all the same thing essentially. So Ardiaz, Lopez, Gandhi, and Quint call it valuations are independent of n. Athey and Hale call it exogenous participation. Roberts and Sweeting refer to it as non-selective entry, and it's just this idea that the distribution of valuations, or the demand essentially, is the same even if the number of even if the number of bidders is different between auctions. And this won't necessarily hold if you were to think about the entry process into the entry here, meaning the bidders who decided to become, or the potential bidders who decided to become actual bidders and participate. So consider this framework where there's a set of potential entrants for each auction, and if they pay some entry costs, they can bid. If they observe some signal about their values before entering, then it's unlikely that valuations are going to be independent of n. There might be some sort of selectivity into the auction here. And when you know the bidder exclusion effect, then this is testable. This is something you could test. And the idea is just that consider first here just a private value setting, so where it's a button auction, so your bids equal your values. Then the bidder exclusion effect, this delta of n is going to be equal to delta of bid. It's going to be equal to 2 over n times the expected gap. So these two things should be equal here. The actual change in revenue between n bidder auctions and n minus 1 bidder auctions, which required n and n minus 1 bidder auctions you had to observe both of these in the data. This is two different kinds of auctions, one where there were n bidders and ones where there were n minus 1. On the right-hand side, it's only n bidder auctions that we're using, and just taking this expected gap between second and third order stats. Those two things should be equal in a private values button auction, and if they're not, then you can reject that valuations are independent of n. So there's one way that you can use this bidder exclusion effect as an interesting test. This is where we simulate an entry model and we say let's do this with all the bids and see how I'll just skip this actually. I'm not to go into the details. But it's just where we describe that ours is almost as powerful as that, and that test is kind of infeasible in ascending auctions to actually use all the bids. We haven't compared it, though, to just using some random subset of the bids, but that's the idea. So you can also use this bidder exclusion effect, though, to look at the to relate to the Bulow-Klemperer idea. So there's this large portion of the literature, in theoretical and empirical literature, where we care about addressing this idea of reserve prices and how much they matter and what are the optimal reserve prices and computing them. And the question remains, how important are they actually in practice? And Bulow and Klemperer have this result that says the seller gains more from having a random bidder show up than from using the optimal reserve price. And one criticism of that result that people have made is they said, because Bulow and Klemperer then go on to say, so maybe this means you should advertise, focus more of your efforts instead of on optimal auction design, focus your efforts on getting more bidders there. And one criticism of that result is you might not get a random bidder to show up by doing that. You might get some sort of marginal bidder to show up that has a low value. We're exploiting the result in a very different way, and we're just saying we observe the effect of randomly removing a bidder, and that the bidder exclusion effect. Sorry, we can estimate the bidder exclusion effect, and that's going to be an upper bound on how much reserve prices should matter. And this is what we get is the effect of removing a random bidder, and they're talking about the effect of adding a random bidder. That's going to be enough. So this is the assumptions we use are that it's a private value setting with low bidding or a common value setting button auction. Those are the two most general ones we can think about. And this second one is what you just stated, Eddie. The change in removing a random bidder is going to be have a bigger impact than adding a bidder. So this gives us a nice upper bound on the effect of using reserve prices. We can also get some nice effects of how much would a seller get hurt if the bidders were to collude or merge. And the assumption we have to make in this case is it has a different meaning whether you're thinking about mergers or collusion. But the assumption is that this merged entity. So if you have after the merger happens, then we're going to say all the other bidders they're still willing to pay at least as much as they were before. They potentially are willing to pay more, but that doesn't really matter. It probably makes more sense just to say they're willing to pay the same. The ones who merge, though, they're also willing to pay at least as much as this merged entity is willing to pay at least as much as the max of the two entities. And this might sound weird. You think, why would they be willing to pay more? Why should they pay more? They should benefit from colluding somehow. They will probably benefit from colluding. They won't have to pay this. This is just what their willingness to pay is. And this in mergers, this allows for production efficiencies. This is like saying you might be willing to pay more now that you've merged. In collusion, what's kind of cool about this is this ties in very closely to these results from the bidding ring literature so Asker's recent paper and then earlier work by Graham and Marshall and co-authors, this paper and also some other ones where they show that a bidding ring is actually willing to pay more than the max of the willingness to pay of the bidding ring members because of at least in the models they consider because of the potential for getting side payments because you have to negotiate how you're going to split the surplus you get from colluding. So this assumption has the same in different meaning, but it's useful in both those cases. And we show that under those assumptions, then you can get a bound on the seller's loss by ends up being 1 over n times the expected times the bidder exclusion effect if the two bidders are randomly selected, or you can get a larger upper bound if the two bidders were non-randomly selected. You might think, why would it be two random bidders that happen to merge or collude with each other? Wouldn't it be the two highest value guys who want to merge? And it definitely would be. Those are the guys who want to merge. But it's going to be hard to convince the other guy that, listen, I'm one of the high value guys. We should merge together. And you can see we show this using Asker's data. We go into look at how often the bidding ring would win if the bidders were randomly matched to be in the ring, and it shows they'd win even more often than they actually do in Asker's data. So and Asker has some intuition for this that it's these low value guys want to get in the ring. They have incentive to participate because you get side payments. There's a chance you'll get some payment from just participating in the ring. So this is one other tool you could use this for. So we go through and apply this to a couple of different data sets. When we look at timber auctions, which is one of the most widely used settings in empirical auctions literature, where people they've made this assumption that valuations are independent of n. They've also studied collusion and mergers, and they've also studied the effects of using an optimal reserve price on the seller's revenue. And in many cases, these models are very complex that they use to attack these problems. And we're able to get at some of the same things they are with just this very simple statistic we compute. So this is just, we computed here the bidder exclusion effect as a percent of revenue on this side, and is just a level on the right-hand side at when there are 3 bidders, and there are 4 bidders and 5 bidders in these different auctions. And so you can interpret this. You can just take any number of those, say with 6 bidders, then the bidder exclusion effect is about 5% of revenue. So that means that you can get from there that an optimal reserve price is only likely to help you at most gain 5% of your revenue. You can also get from that that the expected change in expected loss to the seller from two bidders colluding is going to be 1 over n minus 1 times 5%. So you can scale. You can compute all these different statistics just from this something that's trivial to compute. You can just do this in Excel. Don't even need MATLAB, as we were talking about earlier with Eduardo's papers. Then we go and test this bidder whether the valuations seem to be independent of n, and we're able to. I guess in the interest of time, I'll skip further along. We're able to reject it. The valuations are independent of n. This is just comparing the delta observed to delta bid, and we find that they're statistically significant. So the gap is different. And when we limit this in the second table here, you can focus on limit this just to loggers only. We sort of control for there's loggers and mills in these timber auctions, and we limit to the control for some of these asymmetries, and we're no longer able to reject in as many of these auctions. This is for 3-bidder auctions, 4-bidder auctions, 5 and 6-bidder auctions. So this isn't a huge contribution in itself, the application. We're just trying to illustrate the ways you could use this tool. And then we use it with auto auctions as well. And auto auctions are interesting because you don't observe the number of bidders, as I stated. But we can compute an upper bound on the bidder exclusion effect, averaged over all the number of bidders who must have been there, by just taking the expected gap of second and third order stats and scale it by 2 over n lower bar, which we're going to assume is 3 bidders here, the most conservative estimate you could make given that we observed a third order statistic. We know we observed at least 3 bidders there. And we can compute based on different characteristics. So this is just to illustrate you can do this controlling for numbers of for any characteristic you pick. So this is just non-parametrically estimating conditional on, this is not numbers of bidders, this is some characteristic we pick, this is age. And we do the same thing based on mileage of the car and all these different things. This is 2-year-old cars. The expected gain to a seller from using an optimal reserve price for 2-year-old cars is bounded above by about $150. And for 6-year-old cars, it's bounded above by about $180. So that we're getting an upper bound on whether how interested the auction designer should be in designing the auction optimally, or should they even worry about thinking about it. And for newer cars, you shouldn't worry about as much. For older cars, it is more of a concern. That when you can think of that, it's just because there's less bidders there for these older cars. So we do the same thing with things that represent numbers of bidders, market thickness, and get various numbers here. So in conclusion, then. I'll just conclude with this last slide. Then is you can also get this to compare. I mentioned at the beginning that we started out with this auctioneer paper. So we got a number from that auctioneer paper, which was that using an awesome auctioneer raised expected revenue by about $348, and we found that the bidder exclusion effect was $333. So you can say, you know what? Bulow and Klemper said it's better to have one random bidder show up than it is to use an optimal reserve price. And we say, you know what, it's about just as good or maybe even slightly better to have an awesome auctioneer. So you think of it as a nice little way to benchmark some things. Tedels and Zettelmeyer have this great paper too on information disclosure at these same auctions, and their effect is also is much larger than the impact of an optimal reserve price. So we think this tool can be useful as a benchmarking tool. We also think that just the idea behind it, though, and it being related to the sort of a sufficient statistics approach to auctions here can be used more broadly, and we're thinking about ways to do similar things with bargaining data as well, trying to think about how efficient is bargaining, and can you compute those things without having to make strong assumptions on the equilibrium of the game or on the information environment. So I'll just leave it at that.
All right, thank you, and thanks for the invitation to discuss this paper. I really enjoyed this paper, and let me tell you a little bit why I enjoyed this paper so much. So a theorist typically, here's a caricature of what a theorist might do. Assume a model, design an auction for a model, and then validate that model in some setting to say, gee, this model is, and this design is somehow predicting what we see. And I want to contrast that with how someone in practice who really wants to actually run a mechanism in some specific scenario is going to do. They're going to think about their scenario the first time, have no idea what to do. They're going to come up with some auction. They're going to run it, assess its performance, then adapt the auction given how well or bad it didn't do, and then they're going to repeat. So they're going to basically be running the auctions, trying to assess its performance, repeating, okay, adapting the auction. And what I want to point out here is that if you have a model, then using the theory to design the auction, then great, right? But what if all you have is the data you have from running whatever auction you happen to be running? So the theorist's typical view hasn't really told the practitioner how to actually solve their problem. Okay, and what I really liked about this paper is it addresses this need to give practitioners tools so that when they're running auctions in the field, they can understand, A, what are important characteristics of the model that actually is driving the data they see, and B, how would you think about adapting your auction to improve it so that the next time you're running your auction, you do better for whatever your objective might be. And I think this is a great area for us to be exploring. I think that having this kind of impact, especially in this era of big data, is fundamentally important for us. Okay, and so there are two sort of things you could do here, which I think are great, which this paper does. Identify important model properties. And this paper picked out entry as a really great, selective entry as a property to identify. And the other is evaluate counterfactual auctions. Like what if you were to use an optimal auction with an optimal reserve price? How much do you get from that? So this is, I think, an important area for us to push into, and for auctions or for other areas, how do we give tools to practitioners? Okay, so the paper talked about this bidder exclusion effect, which is the loss from randomly excluding a bidder. And what was nice about this is you can estimate it directly from auction data without having to do things like identify values. Okay, and that actually is really important because methods for identifying values require, well, first, way more data than methods that go directly from bids. And also it involve more assumptions and more complications and more modeling specifics. And if you want to be more agnostic to the modeling specifics, then you need methods like this. Okay, I just point out that I think this area is very important, which is why I have a paper also in this space, which is encourage you to look at it if you feel like it. This paper had three main applications which they highlighted. One was understanding selectivity of entry. The other was bounding counterfactual performance, and the last was identifying the loss of collusion. Okay, they considered a single item setting, setting auction primarily, and many different models of the bidders, and that's actually one of the aspects I particularly liked about it, especially the common value aspect, because it made, I think, it really stress tested the techniques. And in particular, I really found the results interesting when the bids were not equal to values, and that happened when you can have jump bids in this ascending auction. That happens when there's a common value in the auction, and that happens in the appendix of their paper when they studied the first price auction. So I think those parts of the paper where you're doing this estimation when you don't have bids equal to values is especially important. So I want to focus in for the remainder of my discussion on the counterfactual, bounding the counterfactual performance. How well could you have done had you set a reserve price instead? And so in particular, I want to compare the empirical bounds that this paper derives with, which are for the specific setting we have in mind, with just what the worst case bound says over every single setting that you could imagine that has the same parameters. Okay? And so this is the plot that we saw a second ago, which was timber, I guess, right? Showing the percentage of revenue that you could potentially gain by adopting the optimal auction as a function of the number of bidders. And so you might ask, so what about if I said, let's take any distribution, any IID distribution, and ask, what is the potential gain you could get as a function of the number of bidders? Okay, I could analyze that in worst case overall distributions. Okay, so let's do that for regular distributions, which was the assumption also used in the paper. and you get this as the bound. Okay, and so that regular is the declining marginal revenue. Virtual values are monotone. It's the same assumption the Below-Klemperer theorem requires. There is actually a more general condition than Below-Klemperer theorem, but I don't want to talk about that now. But the thing I want to point out, though, here is that we could do a lot of work, look at data, and get these nice numbers, but it's only like, I don't know, 50 to 30% worse to just get the worst case bounds. So actually, in this environment, the worst case bounds seem pretty good. Okay? I want to now make an even stronger assumption on the distribution. What if I assume it's just monotone hazard rate, which, you know, normal, uniform, log normal, exponential. Not log normal? Okay, uniform, normal, exponential. Then you get this bound. That's worst case. So this is actually saying worst case is actually really darn good in these settings. And this is kind of basically what is the Below-Klemperer result saying in these settings? It's saying things are really great. Good. So let me just go into a little bit of details about where this comes from. So let's define opt of n to be the optimal revenue with n agents. SPA of n is second price auction revenue with n agents. So this is what Below-Klemperer is really talking about. The Below-Klemperer theorem says this. The second price auction with n plus 1 is bigger than opt with n. Okay? That's it. Okay? Here's a fact about auctions. The optimal auction with n agents has at least the revenue, at least a 1 minus 1 over n fraction of the revenue of the optimal auction for n agents, meaning if you lose an agent, you lose a 1 over n fraction of your revenue at most. How do you argue that fact? It's actually really easy. So opt of n minus 1 always does better than the following other auction. Simulate the optimal auction with n players by adding a dummy player who you didn't really have. Now, if the dummy happens to win, and they're IID, so this will probably 1 over n, throw out the dummy, and you lose a 1 over n fraction of your revenue. Okay, so that's the proof. Okay, combine these two things together, and you get this theorem, which is exactly the curve I gave you on the previous slide. Okay, so that's regularity. What about monotone hazard rate? So here's a fact I proved in an old paper that's completely a different topic than this. It's that if you have one player from monotone hazard rate distribution, then the probability their value is better than the monopoly reserve price is at least 1 over e. Okay, meaning a constant fraction of time they're above the reserve price, which means the reserve price is binding for them not very often if you have many players. Okay, so let's just call 1 minus 1 over e equal to rho. That's the probability that someone's below the reserve. Good. So for the reserve price to bind, you need all the players to be below the reserve. So that's rho to the n. Okay, so the fact that the reserve price actually excludes players, that's exponentially unlikely. Because rho is a constant. Rho is 1 minus 1 over e. And so as I get more and more players, the fact that the reserve price does anything is just going to 0 so fast. Okay, so you can do a little analysis, which I did this morning, and figure out that this is your bound for the auction, and that's the other curve I gave you. Okay, and this actually, I mean, as I said, I did this morning, so it could be a lot better than this. I don't know. But it's already really good, it seems. And so that leads me to what I think my biggest suggestion for this particular work, which is we need to get beyond single item auctions. So you get these great approximation results that are really good because you're talking about one item and a large number of players. If you were to look in a more general setting with 3 items or 5 items, then the consequence you get from Below-Klemperer immediately gets much worse very fast. Okay, so then your empirical results are going to be much more important and much more like the difference between the worst case bounds and the empirical bounds are going to be much more important to understand. Okay, so I have 2 examples. So just take your usual multi-unit auction, so n players, k items, and unit demands, so each person wants one of them, and think about that setting. And the other one I think is actually a really nice canonical model for thinking about auctions, and that's the position auction model that comes from the ad auction literature, popularized by these papers. Okay, and as an example, what does the Bulow-Klemperer result say for n agents and n over 2 items? It says you have 50% gains from using an optimal reserve, which is huge, right? And so if you had an empirical study which said you're doing much better in that case, then that would be, there's like a large room to actually improve on the worst case bounds here. And Ostrowski and Squirst analyzed this for the log normal distribution and found a 20% loss. And again, these are environments where you have this 20%, remember, compared to this picture, is already up here. It's like way worse than all of these, right? So you're getting, and that's with 6 items. So that's here, 6 and 20, right? 6 players. So I think these are environments where it will really stress test worst case bounds, which then make the empirical bounds much more important and relevant. Okay? So what I'd really like to see in this space is using bitter exclusion-like methods to give better bounds than worst case for these settings where you have multiple items, multiple players, maybe positions with decreasing weights, these kinds of things. Because there, actually, I couldn't see how to apply it from the paper, just knowing the second bid and the third bid, whether that could tell me something about an item auction with k players. Sorry, a k agent auction with whatever, a multi-unit auction. OK, so that's my discussion. Thanks.
So I think it seems like this would be really useful if our main focus were the IPV case. But we're actually, the only part we talk about IPV is a small section of the paper, and then throughout the rest of it, we say, let's let there be correlation, let's let there be common values. And in those cases...
So remember, my corollary there was putting the theorem and the fact together. The fact distributes symmetry, okay? And the theorem was the Bulow-Klemperer. And so the corollary should apply to any case that was not just the IPV model. And yes, the Dubny paper did a bunch of other things that required IPV, but not this one.
Okay. Yeah, okay, so that's not obvious because as we looked at it, we could see that there was a bunch of things we could do if we would limit to the IPV case, but we wanted to try to be more general. So I guess, one of the, for example, in the common values case, common values ascending auctions is one where there is no empirical technique out there for getting back, for figuring out, if you don't know the distribution evaluations, for figuring out what the optimal reserve price would be. As far as I'm aware, there's no way to get that optimal reserve price. And yet, so we're getting a bound on how much an optimal reserve price would help you in a case where the structural auctions ledger hasn't even figured out how to figure out what the optimal reserve price is. So it's or even able to get, so that there's results that you can't, even with correlated private values, no one has been able to find a way to point identify the distribution of valuations. And we're getting a distribution of.
I'll point out my proof though. It just used opt. Like opt did whatever it did. Right. It just simulated it with one more player.
So I was just going to say, like, neither of you knows the answer, but if I had to put my money, I would guess Jason's right that this extends beyond it, just because I played around with these CS type bounds enough, and like it has the smell of. Like,
you know the distribution evaluations in doing opt. To compute opt, you knew the distribution you were drawing from.
No. You should check out these types of arguments because I would guess that they don't. They're just very different than the econ type of arguments. Is the point?
Yeah, we're using them. So if you look at the appendix, we're using the WNL paper. We're using some of these other results to prove some of our cases of like you can show that under the Bulow-Klemperer assumptions, you end up getting the change in revenue from removing a bidder. You can prove sufficient conditions for that to hold in an IPV setting. But so I could be totally wrong. I definitely want to look at it. But I guess at first lesson, it seems to me like some of these might be especially useful in the IPV case, and maybe they wouldn't hold. But I could be wrong. And I definitely want to look. And even if it does only apply in the IPV case, I think it's still an interesting bound to think about. So I think that's all I had. Yeah.
I have a question, and I'm right next to you.
Okay.
So I agree. I mean, it seems like the most interesting cases outside of IPV, because that's where doing more direct approaches is hard. But in that case, it seems to me like, if I understood correctly, it seems to me like it's important to know something about the tightness of the bound for the thing you're actually estimating, which is not the bitter exclusion effect, but this thing that is itself a bound on the bitter exclusion effect. So bitter exclusion effect is a bound on interesting things, like the effect of the optimal reserve or the effect of collusion. You have a finite sample estimator or another thing, which is the effect of dropping one bid, which is itself a bound on bidder exclusion effect. But if we don't know much about how tight that part of the bound is, then we've got two pieces of slippage. In some of your examples, that's okay, because you end up being able to say, like, you know, going to the best auction year is better than, you know, more important than these other things, no matter what. But if it doesn't happen to work out that way, then knowing something about how tight these bounds are could be really important.
Yeah, no, that doesn't make sense. It's a lot harder
Like
to figure out.
just to put a fine point on that, like the argument that we didn't know anything about the common value case is not correct. Like, for example, we knew it was bounded by the total revenue you earned. If in a very general set of cases where your expected revenue is monotonic in the number of bidders, we know that removing a bidder is not going to totally shut down the auction. It can't be worse than totally shutting down the auction. So we had a bound. It was just not a good bound. It wasn't a useful bound. Yeah. So the question is, how useful is this bound? That's the piece that I would like to know more about.
Yeah, that makes sense. So we are able to talk about tightness really well in the collusion and mergers case. We were able to say, here's the case that would give you tight, where this bound would be exactly tight. In the Buehler-Klemperer case, where we're allowing for common values, then it is a bit uglier. And
that's the case where it seems to me like it would be harder to get. I don't know if it's most useful. My intuition is the same, that's a hard case to.
No, and if these tools give to us, then that would be awesome. So I will definitely look into it. Cool. Thank you. Yeah.
So following up on this, you know, like Jess's questions, like when the bounds are bad, actually these computer science techniques are pretty tractable for answering this kind of question, because, you know, typically there's like a strong intuition of what's like the worst possible case, and it's actually like a pretty easy case to solve, even if you don't have IPV and stuff like that. So, you know, actually Jesse's suggestion seems pretty actionable theoretically. And then another thing is, you know, going back to Jason's point, you know, I would actually defend, I mean, the worst case bounds are definitely doing a good job, and, you know, like I would look at them, but then, you know, also defending Brad's method, just like from a business perspective, just because it's a thing that you can do in Excel, you know, you might as well, you know, actually do the Excel.
And it involves data. And it involves data. Like, you know, if you say something's based on theory, no business person would believe it, even if it's tighter than something that's based on data.
But it's based on data and theory.
Yeah, no, I know. I just make a good joke.
But you can tell them that it's not actually.
Yeah, exactly.
You
Just
can tell
tell
them
them
it's just data in itself.